Thanks to the Simons Foundation for the opportunity to present this material to you. Physicists and mathematicians have some things in common. I guess one is that many people don't know what they really do. But they don't actually talk to each other that much. But there have been times, and times in the past and times now, when they do interact. So you could go back to Newton and the invention of calculus. Certainly Einstein's theory of general relativity involved new concepts of geometry being brought into and applied to physics. More recently, string theory has informed and generated new ideas in the study of geometry. And as Yuri mentioned, there's a group of mathematicians and physicists who are at a 3-day meeting now trying to explore the idea that number theory should have something to do with physics. And many public lectures on mathematics try to present some particular result in a kind of simplified way. I'm not really doing that, although I'll mention some specific results. I rather want to try to get across the idea of a mystery that we're trying to solve that involves connections between number theory and physics. So I'm going to organize this talk according to 3 main themes. Those themes are quantum mechanics, symmetry, and number theory. And the first half of the talk, I'm going to say a little bit about each of these topics. Now, each one is a huge topic. I could pick a subtopic and spend the whole hour talking about it, so I'm just going to skim the surface of each. But I'll hopefully skim the surface in a way that allows me to connect them together during the second half of the talk, when I'll talk about 3 topics where these 3 subjects inform each other and are mixed together. The first one I hope will be pretty understandable. The second one will be more difficult, and the last one will be things that I don't really understand myself, but I'll try to say a little bit about them. So I'm going to start with quantum mechanics. And if you look in Webster's dictionary, quantum means a discrete quantity of energy proportional in magnitude to the frequency of the radiation it represents. So this nomenclature and the idea really goes back to discoveries in atomic physics. I've shown here the energy levels of a hydrogen atom. And the thing that's very notable about this compared to what you would expect in classical physics is that the energies are not allowed to take arbitrary values. There are only specific allowed energies. And we know that when an atom makes a transition from one energy level to another, it emits light or absorbs light, depending on whether it's going from a higher energy state to a lower or lower to a higher. And in a hydrogen atom, this emission or absorption of radiation down to the ground state is radiation in the ultraviolet that we can't see. Then there are some other transitions that are in the visible, and these different transitions would correspond to different colors of light. And then there are transitions here which are in the infrared. Now, as I said, this really does not fit in at all with classical physics. And the person who first puzzled over this in a way that led to quantum mechanics was Heisenberg. I've shown you a picture of him here. This name is famous from a certain TV show, but I don't want you thinking about that. I want you thinking about Werner Heisenberg here. So in the mid-1920s, Heisenberg was suffering from very bad hay fever. And to escape the hay fever, he went to a tiny, tiny island called Helgoland in the North Sea. And he spent his time hiking, trying to understand how he could reformulate mechanics in a way that would be consistent with this funny discrete structure of the frequencies of light that were absorbed or emitted from atoms. And he memorized poetry, which was some of the late poetry of Goethe. Now, I'm not a historian of science, so I don't know if this is really relevant or not, but I think it's quite interesting that he was memorizing poems, and these poems have a lot to do with the interaction between East and West, between the relationship between Islam and Christianity. Goethe was fascinated by this. The other thing is that Goethe was a great critic of Newton. Goethe wrote a book on the theory of color that basically said Newton's theory of optics and light was wrong. He tried to overthrow Newton's theory of light. Scientifically, he didn't succeed, but it makes me wonder whether Heisenberg, who was trying to essentially overthrow Newtonian mechanics, was memorizing these poems and hoping to get some inspiration for how to overthrow a different part of Newtonian mechanics. So he came up with something called matrix mechanics, and his insight really seems to come out of the blue. It's not easy to track it back to something else in physics. But he wanted to formulate the theory purely in terms of the things that were observable. Since classical physics didn't give the right idea, maybe the ideas of classical physics, that you would have an electron orbiting around a proton in the hydrogen atom like the Earth rotates about the sun, maybe that wasn't the right idea. You shouldn't think of a position or a momentum. Maybe you should just talk about the things that you could observe, and what were observed were transitions from one energy state to another. So he decided to assign quantities to each pair of energy states. I'll just call them M here, but they would be labeled by the different energy states. And then he wrote down some equations which related these quantities M to each other, that by manipulating he could get predictions that he liked and thought would help him to explain these atomic structures. So in a way, what he did was he took calculus, which is the mathematics of change that was used to formulate Newtonian mechanics, and he replaced it by a much more discrete kind of algebraic, almost number theoretic structure, this algebra of matrices. And he said later that it was 3 o'clock in the night when he finally wrote down the equations that made him think he'd done the right thing. And he was so excited that he couldn't sleep, so he got up and he went and found a rock, and he sat on the rock until the sun came up. That must have been an amazing feeling to have discovered the idea, basic idea behind quantum mechanics. Now, actually, Heisenberg didn't know that what he was manipulating were matrices. Matrices were something that were pure math and not known to most physicists at the time. And it was only when he gave a manuscript to Max Born that Max Born said, these look like matrices that those mathematicians talk about. And sure enough, they were. All right, so the second theme is symmetries. And I'm sure that there is a long history here as well, which I'm not going to try to say much about. But clearly there are things that exist in nature. The Greeks knew about platonic solids and crystals that we can observe in nature, like I think this is iron pyrite, clearly have symmetrical shapes. But it was fairly late on in mathematics that the actual definition of what it meant to be a symmetry was formulated. And I want to give a very simple example here involving not some three-dimensional crystal, but just a two-dimensional square. So if you take a square, and I've labeled the 4 corners A, B, C, D, you can rotate it by 90 degrees, and it still looks the same. I mean, the labels have changed because I put the labels on so that you can keep track of what's happening. But if I didn't have the labels on it, you wouldn't be able to tell the difference between those two squares. So you could say that there's a symmetry of rotation by 90 degrees, and similarly, you can rotate by 100 and 270. And you can also reflect if you take one of the horizontal or vertical axes or a diagonal axis and flip about that axis, the square isn't changed. So there are 8 transformations that are symmetries of a square. Now, mathematicians do something that physicists are always kind of in awe of, which is they take something and they make it more abstract, but at the same time they make it more general, so that the concept can be applied in many different areas. And this idea of a symmetry has been abstracted into what is known as a group, and there are certain axioms of group theory. And, well, I'm not writing them down exactly, but you should think of a group as some collection of objects, which I've called just A, B, C, D, and a way of composing 2 of them such that you get another element of the group, that there's an element that means you do nothing, identity, and that every element has an inverse, and there's also something called associativity, which either you know or you don't, and I'm not going to say anything about it. Now, this group of symmetries of a square clearly has all these properties. There's an identity. I just don't rotate or reflect at all. And if I rotate by 90 degrees, I can then rotate by 270, and I'm back to nothing. So there's an inverse. So here are some examples of groups. So if you've never heard of a group before, you might be surprised, but the good old integers are a group. You can compose them by adding them. 0 is the identity because 0 plus an integer is that integer. And there's an inverse because there are negative numbers. That's what negative numbers are for. There's another group, which we'll encounter later, which is a group of 2 by 2 matrices with integer entries that you multiply in the rule that you use for multiplying matrices. And then, well, I haven't really written it down, But our example of the symmetries of a square is what's called a finite group. There are only a certain number of elements in the group. And for the square, there were just 8 elements, those 8 combinations of either rotations or reflections. All right, and we're also going to need to know something about the idea of a representation of a group. Not very much, but just a little bit. So in this reflection, you can see that what happened is A and D changed places, and B and C were left fixed. And you can think of that as a rule given by this 4x4 matrix that tells you which slot here goes where. So this says you multiply this one by the D, and the D goes up here. So this array of numbers is a rule for telling you what the transformation is. And an array or a matrix like that has D entries up and down is known as a D-dimensional representation of the symmetry group. So mathematicians naturally ask, what kind of groups are there? Can they be classified? And, well, there are many different kinds of groups, most of which I'm not going to be talking about today. But there is one class, this class of groups that just has a finite number of elements. And one of the great theorems in mathematics is called the classification of finite simple groups. So finite means there are a finite number of elements. Simple is a technical word, which basically means it's a kind of a building block that other groups can be made out of. And I guess this is a little bit unfair here, but it sort of started in 1832 with Galois. I've put pictures of Fisher and Grice here, not because they really ended this classification, but rather because they discovered a group called the Monstrous group, which was kind of a stopping point in the discovery of new kinds of groups. So their work will come back a little bit later. And the classification can be written down as a kind of big table, which I found on the internet. I'm not quite sure whether the name over here is the real name of the person that made it or not, but I just liked it so much that I wanted to put it up here. And this upper part consists of infinite columns that label certain kinds of groups. Probably the only one that's immediately familiar is the ones over here. So all of us know how to do arithmetic the way that a clock does arithmetic. You count from 1 up to 12, and then you go back to 1. That's called mod 12 arithmetic. Well, if you do mod prime number arithmetic, like mod 2, mod 3, mod 5, there's a group associated with that, and that's the group that goes down here. Anyway, there are infinite families of these groups that are all classified, all understood in some ways. And then down here, there are 26 oddballs that don't fit into these infinite families. These are called sporadic groups, and we're going to see some of these later on. So this is called a Mathieu group. It was one of the earliest of these groups to be discovered, I think, in the 1860s or so. There's a group called the Onan group, Conway group. These are all named after people. The Thomson group, another mathematician. And then the Monster, which is not named after a mathematician, but was named by a mathematician. All right, so that's my lightning tour of quantum mechanics, my lightning tour of symmetry. From quantum mechanics, I want you to remember the idea of discreteness in the energies and energy proportional to frequency. From symmetry, that there are these weird, very sort of, we don't know where they come from, these sporadic groups. And now I want to say a little bit about number theory. And I'm a physicist, not a mathematician, so I hope I won't embarrass myself too much. So the first thing is you learn that there are a bunch of algorithms and numbers and equations named after Greeks. And certainly our modern ideas of deductive reasoning and how to prove things go back to the Greeks. But number theory goes back further. And so, for example, from the Sumerians and the Babylonians, going back 2, 3, 4, even 4,000 years before the Common Era, our way of telling time with 24 hours in a day, 60 seconds in a minute, 60 minutes in an hour, not 365 days in a year, but the fact that we do things mod 60 and mod 12 goes back to them. And there's an interesting demonstration of this and also of their sophistication in a tablet called Plimpton 322. And I think this has actually been in the news very recently and rather for rather controversial reasons. I'm not talking about that. What I'm talking about goes back to the 1940s. So I think in the 1940s, it was discovered that if you take this cuneiform writing and you interpret it, it's known how to interpret it in terms of numbers. It wasn't completely, they used a sort of base 60, but it wasn't completely base 60. They had symbols for 1, 10, and 60. So anyway, there are numbers in these columns. And in the first row and the second and third columns, there are the numbers 119 and 169. And then in the third row, 4,601, 6,649. Those are curious numbers. What are they for? Well, it turns out that 169 squared is equal to 119 squared plus 120 squared. And 6649 squared is 4601 squared plus 4800 squared. So these numbers have something to do with some rule where you square numbers and they're equal. But the other curious thing is that the number that isn't written down, 120 or 4,800, are divisible by 60. This is 2 times 60, this is 30 by 60. And that's also true for many of the other entries here. So, while there are various explanations of where this fetish for 60 came from, one idea is that it's a very divisible number and it makes it easy to do fractions. There's another theory which I really like, but I don't have quite time to explain, but I'll explain if anybody asks me at the end, which has to do with a clever way of counting on your fingers. So anyway, these are what are known as Pythagorean triples. If you have a right triangle with sides A, B, and C, then there's a famous theorem called the Pythagorean theorem that says A squared plus B squared is equal to C squared. And those numbers are examples of Pythagorean triples where one of the sides of the triangle is divisible by 60. Now, you could ask, how did they find that? I don't think anybody knows. That's probably what part of the controversy is. But I can tell you a way to find such Pythagorean triples. As a matter of fact, to find an infinite number of them. And I'm not going to write down an equation. I probably have too many equations in this talk as it is. But I wrote down a picture, and if you know a little bit of math, you can turn the picture into an equation. So the picture is, let's just take this equation and divide both sides by c squared. Then it says a over c squared plus b over c squared is 1. If a, b, and c are integers, then these ratios are what are called rational numbers, ratios of integers. And the sum of the square is 1. So let's call them x squared plus y squared is equal to 1. Well, if x and y are thought of just as real numbers, and you add their square and equal to 1, that's the equation for a circle. So here's a circle of unit radius, and every point on this circle, x and y, satisfies x squared plus y squared equals 1. It turns out if you take a point on this circle where x and y are rational, and you kind of project, like imagine a light sitting up here, and this light projects an image down to this line, then the coordinate of this point is also a rational number. And conversely, if you start with a rational point here and project back, you'll get a rational point on the circle. So if you just do a little bit of math on it, so to speak, this gives you a formula for finding Pythagorean triples. And it uses a technique which surprisingly is quite common in number theory, at least at my level of understanding, which is you can often turn problems in number theory, which just sounds like, 7, 9, 117, what am I supposed to do? You turn it into a problem in geometry. So I'm now going to try to explain a couple of things that involve doing this in a more sophisticated way. And if it gets a little heavy, I'll just, we'll come back and talk about more down-to-earth things. So the first thing that anybody who learns a little bit of number theory learns is that it's really a hard subject. It's hard in the sense that you can easily state problems that are very simple, very, very elementary, and almost impossible to prove or understand, or sometimes to compute. So a famous example of that is sometimes called Fermat's last theorem, although clearly it wasn't a theorem, it was a conjecture, which is trying to generalize Pythagorean triples to powers greater than 2. So the conjecture is that this equation has no positive integer solution for a, b, and c when that exponent n is greater than 2. And this theorem took about 350 years to prove and involved the development of vast new areas of mathematics. It's been incredibly influential. Here's something a little bit more down to earth, you might think, but it's not. So this is from Facebook. Now, I don't know how many of you are on Facebook. Some of you probably don't waste your time. But if you are on Facebook, perhaps you want to keep in touch with, I don't know, anyway, whoever, you will occasionally get these really goofy math problems. And the math problems usually can be done if you just remember your high school math. And I'm willing to believe that 95% of people do not remember their high school math and can't solve them. And so they usually say 95% of people can't solve them. And then if you do some very simple, arithmetic, you basically get the answer. So I learned about this because a Facebook friend of mine, Zohar Komargatsky, had this appear on his Facebook page just before he was going to take a 4-hour plane ride. And Zohar is a very smart guy and thinks he can solve most problems. So he got on the plane and he tried to solve this problem, and none of his analytic techniques worked. And so he got frustrated and programmed his computer and searched up to, I don't know, something like 1 million values. 4 hours later, he was none the wiser. And he thought, I don't think 95%, about 99.99% of people can't solve this. So I'm not going to solve it in detail, but I'm going to tell you roughly how you solve this equation. So in the same way that you can take those Pythagorean triples and turn it into an equation for rational numbers, you can turn this by multiplying through and simplifying a little bit into an equation for y and x that obeys this equation. Now that's a little bit complicated looking, but if you think about it, it's not that bad. I mean, there's a y squared, there's an x squared like there were for the Pythagorean triples, and then there's this funny x cubed. It's not such a big deal, right? Well, you might say, all right, what does this look like? If y squared plus x squared equals 1 is a circle, what does this equation look like? So you can just get out your favorite program for doing these and say, let x vary over some numbers, and what does y look like? And what you get is this funny yellow curve that has 2 parts to it, this closed part, and then this part, which I really should have shown this going off further, but this line goes off to infinity and down here to infinity. So you get this yellow curve. And mathematicians have discovered something marvelous about these kinds of curves, which are called elliptic curves. They've discovered that they obey what's called a group rule, which says that if you find a rational solution, a rational point, a value of x and y, which are rational numbers, and another one, q, that you can find a third one by a geometrical construction. You draw a line to where it intersects this guy, and then you drop down this across the symmetry axis, and this is p plus q. And algebra tells you that this, is also a rational point. And you can do even better because you can imagine taking this point q closer and closer to the point p, and basically this line will just become a tangent line here, and then you can use that tangent line to add p to itself. So it's not impossible to get from this, to drawing this picture. You would have to find some mathematician to explain the group rule to you. And then you still have some work to do, because with a little bit of searching, you can find an integer solution or a rational solution for x and y. These are small enough numbers that certainly your computer could find them. But the problem asked for positive numbers, and one of these is negative. But you can add p to itself and get 2p, but then a, b, and c are not all positive. So you keep going. You keep going. When you get to 9p, a, b, and c are all positive. This is the first solution. And a, b, and c are roughly 80-digit numbers. 80-digit numbers. 80-digit positive numbers. There's actually a math paper by this, and there's some posting online where I learned some of this. So if on the right-hand side of that equation, there was a 4, if you replace it by 42, the smallest solution has almost 1 million digits. So number theory is really mind-boggling. There are problems that are extremely easy to state and have answers that are really don't make sense. I mean, how could this be? Physicists would love to find something like this to explain why the cosmological constant is so small. We have numbers that are really, really tiny or really, really big, and it'd be great if we could figure out how to get them out of number theory in the way that this kind of magic appears. So physicists like me think this is amazing and love big numbers, but mathematicians probably regard this as somewhat lowbrow and have more refined tastes. And they're really interested more in the structural questions here. And the structural questions are more, what is this group law? How does it work? How many independent ways can you start with points and generate things? And these are the subject, or the starting point, of a very famous conjecture in mathematics known as the Birch-Swinnerton-Dyer conjecture. If you prove it, you can win $1 million from the Clay Foundation. And the fact that problems involving these elliptic curves are so intricate and complicated is used in modern methods of cryptography. So I believe that when you put the chip on your credit card, which we all do now and have to wait a while, into one of those card readers, it's using cryptography based on elliptic curves to encrypt your information before it's sent. All right, one more slide of heavy math. So here I drew a picture that was an elliptic curve when x and y took real values. We were looking for rational points, so that's q and r. But if you let x and y be complex numbers, then the solution to that equation actually looks like a two-dimensional torus, or a donut, if you want. And there's a fact which I am not going to try to really explain in detail, but will appear later on. And that's that you can think of this donut as a parallelogram where you identify opposite sides. So I have a parallelogram and I identify the top and bottom, I roll it up and I have a cylinder. To identify the other two sides, I take that cylinder and bring it around and glue it back together, and now I've got a donut. But it turns out that if you transform this parameter tau, which labels the shape of this donut, by this transformation where a, b, c, and d are integers and obey this condition, you get the same shape back. And this is actually that modular group that I mentioned, again, showing up. So this is perhaps the first hint of a connection between symmetry and number theory. That is, a particular class of problems in number theory involve this kind of symmetry group. All right, so take a slight break from the heavy math. And I now want to explain three problems, or three examples, where these three ideas play together with each other. I'm going to start out by talking about partitions of numbers, and I'll relate that to symmetry, to quantum mechanics, and to number theory. And then we'll get on to things that showed up in the title of this talk, Moonshine, and finally a little bit about black holes. So the idea of a partition of a number is pretty straightforward. It's simply the number of ways of taking a number and breaking it into smaller sums of numbers. By number here, I just mean a positive integer. I'm not allowing negative numbers. So for 4, let's say, 4 is equal to 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. So if you count up, there are 5 ways to partition 4. So let P of n be the number of ways to partition n, to write it as a sum of smaller positive integers. Now, a neat trick is to keep track of these partitions all at once, so you don't have to keep remembering them. So you sum P of n times q to the n. So you get some series here, but you can just, right now, think that the exponent here is telling you what number you're looking at the partitions of, and the number in front is the number of partitions. This is just a formal bookkeeping device at this point, but later on we'll let q be a complex number. So, all right, now that was a little bit of number. Now we have a little bit of quantum. So take a piano, find one of the strings that go back from the middle C, and hit middle C. What happens? It vibrates, you get a tone, but it's not a pure tone. It's not like a, I can't really imitate it. I can't sing it on, I can't sing a sine wave, but you know what a pure tone sounds like. It's very mechanical sounding. So what happens is that that string is tied at both ends, and part of it will just vibrate at the lowest possible frequency, which is middle C, but it can also vibrate a little bit in such a way that it has one node in the middle, and that corresponds to the C above middle C. It can also vibrate so that it has 2 modes in the middle, 2 nodes in the middle, and that's the G in the octave above middle C, and so on. So a real piano string vibrates at all these harmonics, mainly so that you hear the middle C, but you have a rich tone because it has an admixture of all these higher frequencies. So now I want to consider quantizing this piano string. Well, we don't really have to do anything very fancy because we already know what a quantum is. It's a unit of energy proportional to the frequency. So we can write down what the energies of this quantum piano string are. Omega here is supposed to be the frequency of middle C. There's a quantity called h bar, which is the proportionality constant. And the energy, ignoring this a half, which I'll come back to, is just n1, the number of quanta in this middle C mode. Similarly, for the C above middle C mode, there can be n2 quanta, but the frequency is now 2 omega. And in the third mode, you have n3 quanta with 3 h bar omega, and so on. So if you had a particular vibrational mode of the string, the total energy would just be n1 times 1 plus n2 times 2 plus n3 times 3, et cetera, h bar omega, plus something I'm ignoring for now. And if I call this whole thing capital N, you can see what I've done is I've just partitioned N. I've written N as n1 ones plus n2 twos plus n3 threes, et cetera. All right, now we have to face up to something a little bit unpleasant. In quantum mechanics, because of the uncertainty principle, something can't be well localized and not moving at the same time. And that means that there's always a certain amount of ground state energy in any quantum mechanical system. And in this kind of harmonic oscillator vibrational system, that ground state energy is a half h bar omega. And if we only had one mode, that would not be a problem. But if we have an infinite number of frequencies that this can vibrate at, then we ought to add up all these a half h bar omegas plus 1 plus 2 plus 3. I'm calling that the 0-point energy. 0-point energy. I'm calling it the 0-point energy. Now, this 0-point energy is 1/2 h bar omega times the sum 1 plus 2 plus 3 plus 4 plus 5 up to infinity. I think we all know that doesn't make sense. It's infinite. You can, that is not a sensible answer. Now, there are 2 ways of dealing with this. I think a physicist faced with this problem would say, it's a piano wire, stupid. It's not a quantum string. It's a piano wire. And when the frequency gets very, very high, the wavelengths get very small. And when the wavelength is small as the size of the atoms in the piano string, your approximation breaks down. So you ought to just, not sum up to infinity. But I want to imagine that this is a piano made out of superstring. And I'd like to know whether it makes sense. So if this piano is made out of superstring, then we really have to make sense of this. But luckily, the mathematicians tell us what to do. So this is the first place where Ramanujan appears in my talk. And he will appear elsewhere. He was the subject of a great movie, The Man Who Knew Infinity, who our own Ken Ono played a starring role in advising him on the math. But I want to talk about his letters to Harvey. So as you probably know, he was a clerk in India. He basically dropped out of college because he wasn't willing to do anything other than math. He wrote to several English mathematicians and got very dismissive replies. And then he wrote to Harvey. And Harvey, along with some help from Littlewood, realized that he was doing remarkable, amazing things, but he wasn't proving anything. He was just stating certain results. So they wrote back to him, encouraging him, but saying, we need some proof. We need to know what you're doing. And Ramanujan wrote back in a second letter to Harvey, which I think is really quite remarkable. And in part, what he said was this. I told him that the sum of an infinite number of terms of this series, exactly the series we face here with this 0-point energy, 1 plus 2 plus 3 plus 4 is equal to minus a 12th under my theory. And then he goes on to say, basically, you're not going to be able to follow my methods of proof. They don't fit in a single letter. And just verify them. And he says verify them in a somewhat dismissive and arrogant way to me. He says, verify them got by treading on the groove in which the present-day mathematics move. He clearly thought he was treading on some new kind of groove. And indeed, he was. So I just love this because, well, anyway, here he is, this clerk, and he's writing to this very eminent mathematician, And he says, I don't need to prove it, just verify my results. So we'll use that result. Ramanujan eventually went to Cambridge and worked with Harvey, and one of the things that they showed was that for very large n, the number of partitions has a exponential growth. They found this very lovely formula, and then there's some very nice extensions of this that play a role in various things that are going on at this conference. All right, so back to our piano string. So this 0-point energy, I said, was the sum of all the integers, h bar omega over 2. We'll follow Ramanujan and place that by minus a 12th. There are ways of making this more rigorous. I'm not trying to claim that this sum actually makes sense. Some of you probably know of a controversy involving a certain number file video where physicists made various kinds of illegal manipulations with divergent series. I'm not going to do that, but I'll just say that there's a mathematical way of making sense of this, and physically it gives the correct answer. There are actually observable effects related to this treatment. So the other thing we can do with our piano string is we can compute what physicists call the partition function, which is essentially a sum over all the states of the system weighted by an exponential of the energy. And we saw that the number of states with a given energy, n, in units of h bar omega, was just the number of partitions of n. So this kind of generating function that we use to keep track of p of n is exactly this partition function of this quantum piano string, up to a funny factor in front, which comes from this 0-point energy calculation due to Ramanujan. And this turns out to be a known mathematical function, or 1 over a known mathematical function, called the Dedekind eta function. So you don't need to know what the Dedekind eta function is, but again, you could just use some software and you could ask, what does it look like? And I should have mentioned here that I'm making some little change of variables. So these are plots that I did. They're not terribly sophisticated. They're plotting the absolute magnitude of eta as a function of a parameter tau, which is related to q in this way. So on this plot, what you see, other than some colors, is a periodicity that the same pattern repeats when you shift over by 1. From 0 to 1, from 1 to 2, the pattern repeats. Now, there's something interesting going on near the bottom here. So if you take this and blow it up, you get this second picture. And there's still something rather interesting going on down at the bottom. If you take that and blow it up, you get this picture. And there's still something interesting going on down at the bottom, although I think I should have used better resolution in plotting this. And what's going on is that this is an example of what's called a modular function. So that periodicity that we first observed is because when you shift tau plus 1, the function comes back to itself up to a simple factor. And all that other structure is due to the fact that if you take tau to minus 1 over tau, it also comes back to itself. And you can combine these transformations to generate these modular transformations I talked about earlier. So there's a group at play here, this modular group. And I'm sorry if I've written down too much math and too many equations, too many matrices. There's a way of thinking about this just in terms of pictures. So human beings like periodic patterns. Here is a wall tiling from the Alhambra. So this is a way of making a kind of two-dimensional crystal on a wall, which is flat. And here's an ancient pot, which is also covered by a kind of crystal, but one that has to fit on the surface of a sphere, something that has positive curvature. There are also spaces that have constant negative curvature. They're harder to visualize, but they fascinated Escher, who made many drawings based on them. And what you have to imagine is that his famous drawing of devils and angels, as you go out towards the boundary, there are more and more devils and more angels. Imagine that you kept track of how big things were by kind of expanding things as you go out towards the boundary, so that every devil and angel actually has the same size. That would correspond to measuring distances such that the space has constant negative curvature. And modular functions are essentially functions that when you make this kind of transformation from one devil to the angel, come back to themselves. All right, so that's my quantum piano string. And the next example I want to talk about is Monstrous Moonshine. So we've encountered a modular function now in this piano string, a function that comes back to itself, I said up to a factor under this transformation. But there's a very special function which is just completely invariant when you do this, called the modular J function. And once you fix a kind of leading behavior, it's uniquely determined, and it has an expansion in this variable Q. And this thing has two kinds of symmetry, one which was known for a long time, and the other which was discovered more recently and is miraculous. So the one kind of symmetry is the modular symmetry. The other symmetry has to do with this monster group of Fisher and Grice. So this coefficient 196884 was noticed by John Mackay to be 196883 plus 1, but the amazing thing was not his ability to add 1. It was that this number 196883 was the dimension of the smallest non-trivial representation of the monster. Now let's unpack that for a minute. So I told you for the symmetries of a square, you could think of a representation as just a set of 4x4 array of numbers that tell you how the corners transform. So in a way, a representation is just some object that the group can act on, something that's sort of invariant under it. Well, there are groups that are very big. The monster has something like 10 to the 54 elements, which seems ridiculously big. But there's also a group associated with a deck of cards. If you take a deck of cards and shuffle the cards, you're just permuting the cards. That permutation of the cards is also a group. It's bigger than the monster. So why are we not jumping up and down about shuffling cards? Well, a deck of 52 cards has a nice representation with of size 52 by 52, because you can just keep track of how the cards get shuffled. The smallest space that the monster can act on has dimension 196883. It's kind of crazy, even to imagine how you show that, but it's true. And so the fact that that number shows up here maybe is not an accident. Then a little bit later, I think by John Thompson, it was noticed that the next coefficient here is also a sum, and this is the next highest dimension representation of the monster. And I learned recently from Dick Gross that he was at a conference where this fact was sent by mail to someone at the conference, and the letter was passed around from one mathematician to the other with great hilarity. They decided that the finite group theorists had finally gone off the deep end. This was just a sign that they were just off in some never land. It was so ridiculous. There is no reason to think that this modular J function, which shows up in all sorts of number theory, should have anything to do with the largest sporadic group. It was an idea that was so ridiculous that it was called moonshine. Not necessarily the kind of moonshine that you make it a still, but I think more the British, I don't know if it's British or American, moonshine is something that's very foolish or fanciful. And this name moonshine has stuck with the subject, even though it's become more serious and more respectable. So how is this possible? And what did I do with my pointer? I put it down over here. Well, there's an amazing story. It's not really my main story, and so I'm just going to try to say very quickly how it works, or what went into it. So Mackay and Norton here made some of these first observations, and then John Conway and Simon Norton in 1978 wrote a paper called Monstrous Moonshine. These connections that had been observed were turned into much more detailed statements, and they made some precise conjectures about the relationship of the monster to various kinds of modular functions. And then in 1984, Lepowski, Frankel, Lepowski, and Merman constructed an object called the monster VOA. I'm certainly not going to try to tell you exactly what it is or how you construct it, but one way of saying what it is, it's a string moving in a certain 24-dimensional space. And it turns out that the string moving in this 24-dimensional space has a much larger symmetry than just the space. It has the monster group as its symmetry. And the connection to the modular symmetry is that the partition function of this theory, this thing that we computed like for the quantum piano string, which involved the Dedekind eta function, is this J function from the last slide. And then in 1992, Richard Borcherds proved the main conjecture using some techniques that he invented himself and some techniques that came from string theory. So really all I want you to remember about this is that there's an object called the monster VOA. And it is the object which connects these two kinds of symmetry, modular symmetry and the monster symmetry. It's a solution to string theory which exhibits both symmetries at the same time. It exhibits the modular symmetry basically because there's an underlying torus connected to it. And the monster symmetry, we don't know really why it exhibits it, but we can show that it does. All right, so now we're moving more and more towards things that I understand less and less. And so now I want to say a few words about black holes and Umbral moonshine. So black holes are supposed to be black, right? They don't radiate, that's where they got their name. But we know, due to work of Bekenstein and particularly due to work of Hawking, that that's not correct. Black holes actually radiate thermal radiation at a temperature which is determined by their mass. For big black holes, like the ones that LIGO is looking at, that temperature is so low that it's probably not measurable even if we happen to come across one. But as they shrink down, that temperature would go up and up. So this discovery means that black holes really should be thought of as some kind of thermodynamic object, like a hot oven. There should be a temperature, there should be some microscopic description, and there should be an entropy. And entropy is kind of the measure of disorder. And for a black hole, there is a computation in general relativity of what this entropy should be based on analogies between general relativity and thermodynamics, which says it's the area of the event horizon of the black hole. The event horizon is the sort of point of no return when you can't come back out, and a ratio that involves all the fundamental constants of nature. C cubed, c being the speed of light, Planck's constant, h bar, and g being Newton's constant. So in this one little formula, there's geometry, the area of the horizon, there's special relativity, the speed of light, there's quantum mechanics through Planck's constant, and there's gravity through Newton's constant. It's a remarkable formula. But if black holes really behave like thermodynamic objects, there should be an analog of statistical mechanics, which tells us how to go from a bunch of atoms moving around to a temperature and an entropy and a description at large distances. So in statistical mechanics, this entropy is supposed to be the logarithm of some number of states that tells you how many states are compatible with a certain mass or angular momentum or numbers that characterize the black hole. So Andy Strominger and Kumran Vafa found a very beautiful way of realizing this idea in string theory. So what they did is in string theory, there are extra dimensions, there are all sorts of complicated strings and branes, and they wrapped them up in a certain way that gave you an object which had some mass and some charge and some angular momentum. And then they showed that you could vary a parameter, and as this parameter varied all the way to one side, you got something that should really be described as a black hole. And as a black hole, you could compute the entropy in general relativity, but in this description, you could compute it basically by doing a kind of number theory computation by counting the different excitations of these strings and branes wrapping the space. And what they found was perfect agreement. So we don't know if string theory is a correct description of the real world. There's too many solutions. We don't know whether we can get weak and strong electromagnetic interactions out. But all the solutions to string theory have gravity. And this seems to be good evidence, or some evidence, that string theory is at least a correct theory of quantum gravity being the experimentally least accessible part of the world that we know. So then, in 2010, Oguchi, Oguri, and Tachikawa were studying one of the ingredients that went into this calculation of the black holes. They were studying a particular kind of stringy version of a topological invariant, and they showed that it contained a certain object, which is called a Mach modular form. I'm not going to define that for you, but it was also invented by Ramanujan and explained in the very last letter that he wrote to Harvey. He wrote down a bunch of examples of these. He still hadn't really learned how to prove things, or at least didn't want to prove things. He just wrote things down, stated some things, but didn't explain it. And they noticed another kind of moonshine. So there's certain numbers here that are related to representations of one of the first sporadic groups to be discovered, the Mathieu group M24. Well, this whole black hole counting formula gets more complicated, and a number of people have worked on it. And this picture probably doesn't make too much sense, but what I want to give you the idea is that it's complicated, and it's complicated for the following reason. You start with one configuration, then you try to take a limit, and you hope to get a black hole. But it turns out, and I think this was first shown by Frederick Deneff, that there are solutions in string theory that have the same charge, mass, and angular momentum, but correspond to two separated black holes. And if you get two separated black holes, then you're not really counting the right thing. You would like to just count the entropy of one black hole. So after work by a number of people, including some here in the audience that I'm not mentioning, there was a paper that gave a very nice mathematical setting for what was going on here by Dabelkar, Murthy, and Donzage called Quantum Black Holes, Wall Crossing, and Mach Modular Forms. And it was really this paper that got me interested in this whole subject that I'm discussing now. Tish was a former graduate student of mine. And what they showed is that the Mach modular form, like the one that Oguri, Gucci, and Tachikawa found, came out by trying to separate out these single center black holes from the double center black holes. And their paper was really a kind of a starting point for an investigation that Miranda Cheng, John Duncan, and I did of trying to extend their results and see whether there are other kinds of moonshines involving these Mach modular forms. And there was a very nice Quanta article by Erica Klarich, which shows a picture of me and John and Miranda on top of some kind of an island, which I think is supposed to be made out of a K3 surface. And Ramanujan is over here taking notes, sitting on top of these disks that have constant negative curvature. So we found a list of mathematical objects that generalize the Mathieu M24, generalize the Mach modular form, and we showed that there were 23 of these. So I'm not really going to explain what this was in any detail. I'll just say that it's a more refined kind of moonshine, a more extensive kind of moonshine, but for other kinds of modular forms. And it has links to all sorts of interesting aspects of both string theory and mathematics, lattices, groups, and geometry. I don't think we really know what it comes from yet, but we have been able to find a lot of mathematical results. So this kind of brings me to where we are now at this conference, and we're now investigating what you might call a kind of third wave of moonshine. We are investigating, we're hearing about moonshine for other kinds of groups, another one of the sporadic groups, which is interesting because it's not really connected to the monster group, all sorts of mathematical objects like L functions, and well, anyway, lots of interesting things that are expanding our horizon of what moonshine is. But we don't really, we have a mystery. We don't fundamentally know why these functions that appear in number theory and these objects that occur in counting black holes and in some physical systems, we don't know why they're connected. We don't know what's going on. So we have some goals, or at least, well, I'm sure we all have our own goals. These are my goals as a physicist who occasionally dabbles in mathematics. So I'd really like to find some explanation for the origins of moonshine that would give a conceptual reason for why these sporadic groups are showing up and what's going on. The monster VOA, which I didn't define, but I told you was this magical object that allows you to connect these two kinds of symmetry, is something that we don't have for these other examples of moonshine. If we had it, we could prove theorems, we could probably understand new things about string theory, we would have some great new constructions, but we don't have them. It's perhaps a little bit of a fantasy, but I think there may be some new approaches to aspects of number theory that come out of this. Certainly, many of the things that people are finding are connected in number theory, And if they show up in a more physical setting, like string theory, well, string theorists are not hampered by having to prove theorems and having to do things rigorously. We are happy to wave our hands, compute using things that are ill-defined, and often get the right answer. And by doing this, we sometimes give mathematicians ideas that they can then turn into rigorous mathematics. That's happened many times in the past. And I think it's not inconceivable that if we can make the right connections in number theory, some of those tricks can be pulled again. In any event, I think we'll find some very new and nice connections between geometry, number theory, and string theory. And so it's really fun and exciting conference, and we're all having a great time, and thank the Simons Foundation for being here. So I'd like to say thank you and be happy to take any questions.